Okay, but before jumping into the analysis with Karamba, let's take a closer look to what the fast-formal book has to say about truss structures, right? So as we can see here in the left side of the screen, we can either have compression forces, which are drawn in red color, or tension forces, which are drawn in blue color, right? And basically, we are going to see that the lower cord is always under tension and the upper cord is always under compression. And the reason for that is that basically the bending moment is broken down into these couple of forces, right? Tension forces here and compression forces here. For that reason, we don't have bending moments in our truss bars. We just have compression or tension, right? And not only that, but also the orientation of the diagonals, they play a very important role to define whether they are in tension or in compression, right? So in this case, in the book, it is explained in that way that if the diagonals, they follow the shape of a cable line, right? They are more or less parallel to a cable line. They would be under tension. However, if they follow the shape of an arc, let's say, then they could be under compression, right? And this is very important because, as we are going to see, we are going to optimize this structure later on, and this optimization is going to take into account buckling, right? So buckling is basically this instability effect that happens when cylinder members are under compression. And what the result basically is that members under compression would need a stronger cross-section than members under tension, but for the same force and for the same member length, right? Okay, so that's something very important to take into account for defining our diagonals, and also that will explain how the cross-sections of the upper cord are somehow bigger than the lower cord. But let's take a look into it later on with Karamba. And finally, we have already identified which bars are going to be under compression and which ones under tension. And there are also some bars that they are not going to have any kind of force at all. And these are the so-called null bars. And there are some tricks to identify them. For instance, here on the right side, we can identify this null bar because we have 3 bars connecting on one joint, but 2 of them have the same direction, which means that this third bar is going to have a 0 force, because otherwise the equilibrium would not be possible, right, at this node. And another possibility for these null bars could be just basically 2 null bars connecting on one joint with a different orientation. And we can also have the case of 2 bars connecting into a node without a load. And in that case, both bars would be null bars, but we don't have this case here. What we have is the third and last case, in which 2 bars connect at one node or one point, and they have different direction, and this node is loaded. So in that case, we would have a null bar in the one that is not along the direction of our load. So in this case, we can see that this is a null bar because we have just 2 bars here, and the force is active in the opposite direction, in the perpendicular direction, I mean. And in this case, it happens the same. We don't have a load, but a reaction force. But anyway, we have 2 bars. So the bar that is coming in the same direction as our reaction force is going to be loaded, and the other one is going to be a null bar. But anyway, let's take a closer look into this with Karamba.